This is ME3260 Spring 2019, Homework 1, Problem 1.2.
Alright, this is being done by Vogeler and Gawry. So the first step is to draw a free body diagram representing the system. So as you see here, we have two cylinders being compressed by an axial force. So first we want to draw a line representing them. So we're going to have the wall, which is obviously stationary, cylinder 1, cylinder 2, and an axial force compressing on the end. There'll be a reaction force between cylinder 1 and 2, pushing outwards on cylinder 2, and then compressing cylinder 1, and then a reaction force from the wall on cylinder 1, compressing that, and then obviously the reaction force on the wall. This will result in displacement of 0 at the wall. And then the piece connected to the wall will obviously be displaced 0 because the wall is infinite mass. The displacement of the end will be x1, and we're defining this as the positive direction. And then the line between cylinder 1 and cylinder 2 will define as displacement x2. And those are both in compression, so the direction is to the left. I'm going to go ahead and label the cylinders, cylinder 1 and 2. And then before we continue, we want to be able to convert these two cylinders into springs to simplify the system. So we're going to derive the equivalent spring constant of the two cylinders. This comes from Hooke's law, which is sigma equals E times epsilon. So sigma is obviously stress, is equal to Young's modulus times the strain. If we replace stress with the compressive force divided by the area, which is pi times, here we have diameters, so diameter divided by 2 is radius, squared equals Young's modulus times change in length, so delta x, divided by total length, or L, so that's L1 or L2. And the stress experienced throughout the cylinders will be constant throughout. Now, we're going to rearrange some of these terms to get force by itself. So when we do that, we get force is equal to Young's modulus times pi times d squared over 4L times delta x. And if you look, this equation looks very similar to the equation we use for springs. So F is equal to K times X, where X is the displacement of the spring. And so we're going to define E pi diameter squared over 4L to be equal to K. And this goes for cylinder 1 or cylinder 2. So K1 is equal to, they're both the same material, so both have the same Young's modulus, which is undefined, so we're just going to leave that as E, times pi d1 squared over 4L1, and then K2 is equal to Young's modulus times pi d2 squared over 4L2. Alright, now that we have equivalent spring constants for the two cylinders, we're going to simplify this system and draw it as springs rather than cylinders for our purposes. So obviously we still have ground. Then we have spring 1, spring 2, and we still have the same forces acting upon it. So force compressing the spring at one end, a reaction force between the two springs, equal and opposite reaction force, and then the reaction force is the wall. And then defining our coordinates again, so we still have x1, which is positive, pointing from the initial position of the spring. Then x2 is the position where the two springs come in contact. So x2 there, and x2 here. And then zero displacement at the wall, because the wall is massive and immovable. Now that we have, and as we said, we have a K1 and a K2, so the equivalent spring constants defined above. So now that we have this, we can come up with the equations for the forces produced by the compression of each spring or cylinder. So force is obviously constant throughout, so F is equal to K1 times X2, because as you can see, cylinder 1 is compressed amount X2, and the same equation can be written for cylinder 2. So force is equal to K2 times X1 minus X2, and this is because X1 is in the same direction as X2, or as the force, and then X2 is in the direction opposite the force. Okay, now that we have two equations for force, we're going to set them equal to one another. So we have K1 X2 is equal to K2 X1 minus K2 X2. I took the liberty to expand that. And then we're going to want to solve and get X2 all on the same side. So add K2 X2 over to the left. So we have K1 X2 plus K2 X2 is equal to K2 X1. And if we pull X2 out, we have X2 times K1 plus K2 equals K2 X1. We want to divide K1 plus K2 over the right, so we get X2 equals K2 divided by K1 plus K2 multiplied by X1. And from above, we have an equation. We have X2 times K1 equal to the force. So we want to get force back in this equation to be able to get the equivalent spring force, equivalent single spring force. So we're going to do that is just solve for F up here. So or solve for X2, I mean. So force divided by K1 equals X2. We can plug that in. So now we get force over K1 equals K2 divided by K1 plus K2 multiplied by X1. Moving K1 to the right side, we get force is equal to K1 times K2 divided by K1 plus K2 times X1, which we defined above as the displacement of the right side of the spring, and this is now the equivalent spring equation. So we have F times K equivalent times X, which is the displacement of the right side of the spring, and we're going to go ahead and plug in the variables. And welcome back. Now we're going to plug in K1 and K2 to get our final equation and hope that some things cancel out. So we have Young's modulus times pi times d1 squared over 4L1 multiplied by Young's modulus times pi d2 squared over 4L2. all of this divided by e pi d1 squared over 4L1 plus e pi d2 squared over 4L2. Simplifying this, multiplied by x1 equals force. This is equivalent to e pi squared times d1 squared d2 squared divided by 16L1 L2. And then simplifying the bottom, we're going to pull out e pi over 4. And then what's left is d1 squared over L1 plus d2 squared over L2. And now e pi, they cancel out, and we can cancel out one of the 4's. And what we're left with is Young's modulus times pi times d1 d2 squared. And on the bottom we can multiply L1 and L2 by everything, and you get a little bit of cancellation. So we have d1 squared L2 plus d2 squared L1. All of this gets multiplied by x1 and is equal to force. So the equivalent spring constant for a single spring representing the two cylinders is shown below. Thank you very much, everyone. Have a great day.